Waiting for the computer. Alright. The sun. The great ball of light in the sky. It gives us our energy, gives us our heat, gives us our light, gives us everything we need. And I believe it will also give us the solution to our energy needs. My name is James Miller, and I believe that nuclear fusion has the potential to be the clean and green energy of the future. Now today I will be talking about what nuclear fusion is, how we can achieve that process on Earth, and the fuel used in the nuclear fusion process. So first things first. If you remember during my problem presentation speech, I told you what fission was. Whether you remember or not, I'm going to give you a quick recap. Fission is when you have a big atom, you hit it with a neutron, and you split it into smaller atoms, which are usually radioactive, and it gives off a lot of energy in the form of heat and also gives us neutrons. Fusion, on the other hand, is the exact opposite process. You have two smaller atoms, and you kind of sling them together and make them combine into one larger atom that gives off a neutron and heat, or energy, I mean. Now here we have deuterium, tritium, or deuterium and tritium are the two small atoms, and they give us helium, energy, and neutron as the products. And this will be the form of, or this will be the fusion that I'll be talking about today. There are other forms or other fuels used for fusion out there, but I'll be focusing on this one due to my spectrum of my topic. Now, how fusion and even fission take place is through the process, or through overcoming something called binding energy. Now, Randall D. Knight goes into a lot of detail about what binding energy is in the physics book for 214, but I'm going to talk about it on a simpler scale because it's very confusing. So binding energy is pretty much how closely knit together nucleus is of an element. And as you can see here, this is a chart of the binding energies of all the elements, even some that aren't on the periodic table. And the ones that I want to focus on today are highlighted in red. Now, the one highlighted in blue kind of stands out because it's not highlighted in red, but that is iron. Iron is the most stable element out there for binding energy, and it determines whether or not an element will take place in fusion or fission. If it's heavier than iron, like uranium-235, it'll be used in fission. If it's lighter, it'll be used in fusion, like deuterium and tritium. So from this chart, you can see here that the binding energies are low for deuterium and tritium, and then the product that they create is helium up there. And then the difference between those is very large. So that means that it puts off a lot of energy after it's combined. For fission, on the other hand, it's over there. Uranium-235 is there, and I believe that its baby products are in this gap right there. The gap between them is not that large. It's a lot smaller than the gap between that. So that's why fusion gives off about 4 times as much energy per reaction than fission does because of this difference in gap. This is about 1 or so, and this is about 4. So that's the difference, and that's why fusion would be a better thing, because it gives off 4 times the amount of energy. Now, the sun makes fusion occur because, according to NASA, it's about 15 million Kelvin on the inside and weighs about 2 times 10 to the 30th kilograms. Now, for a comparison, that's about the same mass as 330,000 Earths. Clearly, we can't replicate this process to create fusion because we just don't have that much mass. But what we do have instead is this fancy design, which is called a tokamak. And this allows us to create temperatures high enough to allow fusion to occur. Now, we have to reach about 12 million Kelvin for fusion to take place. And the tokamak does that by heating up the fuel, which is deuterium and tritium, as I said before, and making it in a state that's called plasma, which is kind of like a liquid solid. It's a fourth state, and it's the same state that the sun's in for comparison. Now, with that plasma, it's about 12 million Kelvin, like I said, which is incredibly, incredibly hot. So if it touches the tokamak or anything else, then it won't, or it'll melt it, and then there goes the reactor. So it prevents this through these little orange cylinders around the outside, which are giant electromagnets. They are along the lines of the same thing as a maglev train, where you turn on the electricity and the train floats and that flies like the bullet trains. So it does this through magnetic levitation. There we go. And it does that because it runs a current through these, and then that creates a magnetic field which kind of floats the plasma and has it moving along in a circle around the tokamak, which that allows the elements to hit each other and then fuse, because you can't have them fuse if you don't have them touch. So ITER, which is short for International Thermonuclear Experimental Reactor, is currently building a tokamak in France. Construction started in 2013, that was when the foundation concrete was poured, and construction is expected to be finished in 2019. Now, full-blown deuterium-tritium fusions will not take place until 2027 because they have to work up to that. But I've been throwing around the word fuel, and I've been saying deuterium and tritium a lot throughout the speech, so now I'm going to tell you a little bit about what they actually are. Deuterium and tritium are just isotopes of hydrogen. They are heavier isotopes, and they are seen here. Deuterium has an extra neutron, and tritium has 2 extra neutrons, which are not usually found in hydrogen. Deuterium is very commonly found on Earth. It is located in seawater and can be very easily extracted from that. But tritium, on the other hand, is not commonly found. It has to be created through the use of farming lithium farming, I mean. And that is when you hit lithium with a neutron and it gives you helium and tritium as the byproducts of the reaction. But the problem with that is tritium is radioactive. It has a half-life of about 14 years, which is not that bad in the grand scheme of things, considering that the half-life of uranium-235 is 700 million years. So it's not that bad to think about it. And the only form of decay that gives off is beta, which can be stopped by an aluminum sheet, if you remember from my speech, from my first speech. So those are the ups to all of nuclear fusion. And just as a recap, today I told you about what nuclear fusion is, how we can achieve it on Earth, and the fuel used in a nuclear fusion process. Now, I hope after sitting there listening to me give this speech, you can agree with me when I say that fusion is the future. Thank you for listening, and have a good day. Any questions?